Hi and welcome to this second video of the module. We will continue introducing Rdf, explaining its core components and how it can be serialized. Finally, we will introduce the type of inferences that it supports. One of the main components in Rdf and on all the formats and languages that are built upon it are the URIs or IRIs. These components are strings of alphanumeric characters that serve as the unique identifiers for the data resources we will manage in Rdf. An IRI or URI can be divided into 5 main parts. First, we have the scheme, which refers to the name of a specification with which to assign the identifiers. Often, a protocol is used as the base for this scheme, such as, for example, HTTP, which will be the most used one as it is the base of the web itself. Second, we have the authority that identifies the organization behind the data generated using these URIs. It is often defined by a hostname, but it can be defined as an IP address or even contain information about the users. Then we have the path, which establishes the hierarchical structure of the information within the scheme and the authority. It can be specified, for example, as the path on the server which stores the Rdf data. Then we have the query, which is an optional component for specifying the non-hierarchical part of the URI definition. It is defined in terms of pairs of key value. And finally, we have the fragment, which allows to specify a given part of the overall resource. As you may have noticed, we distinguish between two different terms, URI and IRI. The only difference between both of them is that an IRI can contain Unicode characters. That is, we can introduce specific symbols such as, for example, accent marks or characters from different alphabets. In general, we will use the term URI to refer to both kinds of identifiers. In this example, we see how for each of the resources and the predicates we are defining a URI. So we will have a URI for Raúl using the HTTP scheme within the OEG UPNet authority. We will have as well a URI for the ontology engineering group, the OEG, and for each of the properties. As you may see, literal values such as, for example, strings or dates do not have URIs as they are literal values itself. When defining URIs, we can use namespaces. That is, keywords that define a prefix URI for a dataset. The URIs that belong to a namespace are considered a vocabulary. In this example, we see several vocabulary namespaces for defining information about, for example, people, organization, or the properties of our dataset. We also have some well-known vocabularies such as, for example, Rdf itself, RDFS, or the XSD data types. Using namespaces, we can shorten the URIs of our Rdf resources. We can substitute the first part of the URI by its corresponding prefix. As we see on the example, we have used each prefix for each URI. So we have the people prefix for Raúl or the organization prefix for OEG. As well, we have the properties prefix for has full name or has web page. This saves time when typing, of course, and also reduces the size of the files that we are generating for our dataset. When working with Rdf, we can classify our resources into classes. For that, we will use the Rdf type property from the Rdf vocabulary. By using this property, we can divide our Rdf resources into two different types. Classes defining the concepts and instances defining the individuals belonging to those classes. As we see in the example, we can classify Raúl and Oscar, defined using the people vocabulary, under the person category. In the same way, we can state other kind of resources, such as, for example, animals as seen in this example. We can apply the same principle to classify properties using the Rdf property class. So we see here that has full name and has web page are classified as RDF properties by means of the RDF type property. Sometimes we will need to express compound property values, for which we will have to use something a little bit more complex than a single URI-based resource. For those cases, we can use blank node, that is, intermediate nodes that group compositions of values. For example, if we can state that Raúl has a full name that is composed in this case by a first name and a last name at the same time, as shown in the example, we could do it by generating internally a blank node. Blank nodes do not contain any data, but serve as a parent node for a data group, in this case first and last name. They do not need to have a specific URI, as they are intermediate values. So most of them has a random URI for identifying. All this concept that we have introduced so far, defining how data is represented in RDF, can be codified using different syntaxes. From the very few serializations from RDF 1.0 to the many available for RDF 1.1. What it is important to understand is that even though the syntaxes are different in each serialization, the content remains always the same. As well, it is fundamental to understand that the order of the triples has no effect on RDF. That is, two different files with the same triples in different orders must be considered the same RDF dataset. In this example, we see a small dataset containing information about three persons and how they relate to each other. This fragment of code shows how to represent it in RDF XML. We see the corresponding statements in the code to individuals and properties. In this other example, we see how to codify the same information using the more compact turtle format. Even though they look really different, they contain the same information, and both datasets are the same. But in this case, we have a more compact representation format, which allows to perform a more efficient data sharing when communicating datasets. Finally, we introduce inference and reasoning. When working with RDF, we have the possibility of applying inference. That is, apply rules that, when satisfied, will trigger the generation of new triples. Here we see some of the RDF rules for reasoning that are available. Other languages will define other rules, their own ones, as well. Using external reasoners will allow us as well to implement our own rules. In this case, the RDF1 rule states, for example, that if we have a triple U, A, Y, we can conclude that A must be an RDF property, that is, a RDF type RDF property. A complete list of these entailment rules can be accessed on this website. With this, we conclude the fundamental fabric of the semantic web. In the following video, we will see how RDFS extends RDF.